My name is Chiara Sabatti, and I want to welcome you tonight. This is the distinguished lecture in the that Stanford Data Science supports for the winter quarter. It's the first lecture that we had in this academic year. It's also one of the seminars in the series that we have titled Scientific Discovery in the Age of Data and AI. So I hope you will find the topic of interest. But first of all, I want to welcome you also in the name of the people who really made this event possible. So the Data Science Executive Director, Chris Mansell, and the people that really organized the event, Laura, Maddie, Alicia, Lynn, Alexandra, and Sophia, who have welcomed you as you came in. I also want to extend you the welcome of the director of Stanford Data Science, who is now unfortunately away because he's taking part to the AI summit that's happening in Paris these days. And now, after all of this introduction, I want to remind you how the format is going to be. We're going to have a presentation for 50 minutes or so, and then we have ample time for questions. These are really meant to be events where we talk and exchange ideas, not only in the pre-lecture times where we try to eat something, but also afterwards, really taking advantage of the intellectual stimulations that we get from the lecture. So it is really my pleasure to introduce tonight's speaker, Professor Tom Griffiths. He is a professor of psychology and computer science and the director of the Computational Cognitive Science Lab at Princeton, as well as the director of the Princeton Laboratory for Artificial Intelligence, which is a fairly new organization that is really in many ways analogous to what we're trying to do with Stanford Data Science, in that it tries to facilitates a lot of research in many different areas that deals with data and computation. I mentioned to you the topic of this series of lectures that we have been having, and when we started making the list, the name of Tom Griffiths came up very naturally as one of the main speakers to invite. He has been having a very prolific and interesting career studying how human cognition with mathematical models that we can make for human cognition, but also understanding how human ways of reasoning is different from a machine way of reasoning. What does it mean to reason for a human, for a machine? How should we do that? He's the author not only of strictly scientific publications, but also of a book that we might all enjoy. It's called Algorithm to Live By, and he has received numerous awards. So I don't want to take any more of his time away. Please help me in welcoming Professor Griffiths.
All right, thank you very much. It's wonderful to be here. One of the facts that was omitted from my biography there was that I actually got my PhD from Stanford, and so it's very nice to be back and visit a lot of the places that I was many years ago. One interesting fact about that is that actually while I was a graduate student, I worked with a law professor on a book that was actually about human decision-making, and that law professor was Paul Brest. So it's particularly nice to have the opportunity to give this talk in Paul Brest Hall, and he was going to try and be here today, but unfortunately wasn't able to make it. So it's really wonderful to be able to rekindle some of those relationships and have the chance to visit places that mean a lot to me. So as you heard, I'm going to be talking about understanding human decision-making, and there's a lot of reasons why we might care about understanding human decision-making. One of the classic reasons is that human decisions underlie our economy, right, the sorts of financial decisions that people make. But nowadays, there are many other reasons why we might care about understanding human decision-making as well. So if you're trying to build any kind of system which is going to interact with human beings, it's helpful if those systems are able to make inferences about what it is that human beings want. And one of the ways that you can make inferences about what human beings want is understanding how it is that what people want translates into the way in which they behave. So you can kind of work backwards and figure out what they might want from the things that they do. And if those stakes don't seem high enough for you, we can easily raise the stakes, because those systems that are making those inferences about how human beings are going to act are not just things that you're interacting with your voice or by typing, but things that you're interacting with on the road. This is a photo from a collision that involved a self-driving car from the Uber self-driving car program, where arguably the cause of this collision was not making an appropriate inference about the kinds of things that people know about and can take actions based on the observations that you have of their behavior. And so the focus of the talk I'm going to give today is really on thinking about how it is that we can make machines that might be able to better predict and explain human behavior, and in particular human decisions. So if you're a machine learning researcher, one of the ways that you can think about making machines better at doing something, or at least making it easier for them to learn how to do something, is by thinking about what machine learning researchers call inductive bias. Right? So inductive bias is everything other than the data that influences what a system learns. So it's the kind of the things that you build into a system that influence what it's going to be easy for that system to learn and what things might be hard for that system to learn. Inductive bias isn't necessarily trendy at the moment. The current sort of trends in machine learning over the last 10 years have been more focused on trying to engineer systems that have a large capacity for processing data, so you can feed more and more data into them. You don't need to have much inductive bias in order to get them to learn how to solve problems. But I think as we start to run out of data in certain critical applications, or when we're trying to work in areas like understanding human behavior, where we have limited data and data are expensive to come by, thinking about inductive bias is important. So despite the fact that inductive bias is unpopular, it's something that we nonetheless see in deep learning models. So for example, if you look at things like convolutional neural networks, which are used to learn functions that involve images, like classifying images, they have an inductive bias which makes them particularly good for processing images, right? So they are sort of built in a way which allows them to learn functions that are translation invariant more effectively. Or if we look at things like long short-term memory networks or transformers, they have an inductive bias which makes it possible for them to learn things that involve complex relationships that might unfold in sequences. And so one way of thinking about this is that machine learning has been very successful in constructing models that have good inductive biases for learning things about images or learning things about text. But we haven't necessarily been very successful in creating systems that have good inductive biases for learning things about people. If you want to build a system that is trying to predict something about human behavior, you can't say, oh, I'll go get my neural network architecture, which is particularly useful for predicting human behavior, because no one has come up with that. Normally, when people are trying to make predictions about human behavior, they go and grab a sort of standard off-the-shelf neural network or some other kind of standard machine learning technique. There's not the same kind of understanding of what the inductive biases need to look like. And so that's the thing that I'm going to focus on. And what I'm going to argue is that, in fact, there's a particularly useful source of inductive bias if you want to build systems that can make predictions about human behavior. And that source of inductive bias is the last 100 years or so of psychological research, right? So, for about 100 years, people have been trying to understand how human behavior works. Psychologists have figured some things out. Those things that people have figured out are useful in allowing us to construct systems that have good inductive biases for predicting behavior. And so the first question I'm going to engage in here is trying to answer this question of how it is that theories from psychology might aid us in developing machine learning models. But I'm also going to sort of turn this around, because it's certainly not the case that psychologists over the last 100 years have figured out everything about human behavior. And there's actually a way in which the kinds of machine learning models we build can be equally useful in helping us learn new things about humans, right? So the second question I'm going to engage with is a question of how it is that machine learning can help explain and not just predict human behavior, so help us build tools that help us to make progress in that scientific goal of understanding human behavior better. And in this talk, the focus is going to be on 3 methods for combining theory and data that we've developed in my lab over the last few years that are really focused on this problem of how do we create systems that have the right kinds of inductive biases for making predictions about people, or also in other scientific settings, and how it is that we can constrain models that allow us to be able to learn effectively from small amounts of data, and then how it is that we can build more interpretable models. And so while my focus is going to be on human decision making, the kinds of methods that I'm going to be talking about here are things that I think are actually pretty broadly applicable in solving a wide range of scientific problems where you have limited amounts of data and you have machine learning techniques that you want to be able to use. And so hopefully it's a good fit for the theme of this series. So the first example that I'm going to zoom in on is motivated by this financial case. And I'll sort of use this example for most of the first part of the talk, and then I'll switch gears and talk about another decision-making problem. And so this example comes from thinking about, sort of the most basic elements of these sorts of financial decisions, which is essentially making a decision under risk, right? Making a decision where you've got some uncertain outcomes, there are different payoffs associated with those outcomes, and you're trying to figure out which option you should select under those circumstances. So in psychology and in other fields that have studied decision making, this kind of decision is what's called risky choice. And here's a sort of standard example of a risky choice problem, right? So if you've ever participated in a psychology experiment on decision making, you might have seen something like this. People are taking a psychology class, might be having flashbacks to sitting in a dingy room and sort of having to push buttons on a keyboard, right? So these are the sort of classic kinds of problems that have been used to study human decision making. So in this case, you have a choice between two options. If you choose option A, you get 16 points or dollars with certainty, so with probability 1. And then if you choose option B, there's a different distribution of different outcomes that can occur with different probabilities and then payoffs that are associated with those. And you have to make a decision about whether you want to choose option A or option B in this situation. So these kinds of risky choice problems have been the bread and butter of at least a part of the different disciplines like psychology and behavioral economics that have studied human decision making. They have motivated the development of various theories. They've been used to show that those theories seem to be wrong, and they've given us a certain amount of data that we can use for starting to constrain the sort of theories that we might construct of how it is that people make decisions. And so a natural question that we could ask is whether you can use machine learning models to make predictions about this sort of most basic version of human decision making. So all the way back in 2015, this is really the moment that was the genesis for the work that I'm going to talk about today, a group of researchers at the Technion in Israel, led by Ido Erev, ran what they called the choice prediction competition. And the idea behind the choice prediction competition was that people would see a bunch of these gambles. So they'd see 90 of these gambles, these choice problems where you're deciding between two gambles. And then the data from people's responses to those 90 gambles would then be provided to people who are participating in this prediction competition. And those people could use whatever method they wanted. They could come up with a psychological theory. They could use a machine learning method. They could apply those things to those 90 gambles. And then they would submit predictions, and those predictions would be evaluated against the actual behavior that people showed on another 30 gambles. And so what you actually had to predict, the data that you got and the thing you had to predict were how many people, what proportion of people would choose option A in this situation and what proportion would choose option B. And so you'd see that for 90 problems like this, and then you'd have to make those predictions for another 30. And what they found when they did this analysis was that the kinds of machine learning models performed extremely poorly, right? So when you ran machine learning models, compared them with the intuitions of psychologists, the intuitions of psychologists won every time. The best models for making these kinds of predictions about human behavior were things that were either theories that psychologists had come up with or machine learning models that were very constrained to use features that corresponded to things that psychologists thought were important. And so that was the conclusion of their papers, was that it seemed like you really needed this sort of psychological input in order to do a good job in solving this problem. So a few years later, they ran another choice prediction competition. And this choice prediction competition was in 2018 and had a bit more data. So it had sort of on the order of 300 pairs of gambles, but the same kind of basic prediction problem. Take those gambles, make a prediction, and then you get scored. And a group of researchers from my lab got really interested in this, and we tried to come up with a way of solving this problem. So one way that you can think about exactly what this problem is it's something where you've got an input space, which corresponds to the descriptions of the gambles, right? So you've got all of these outcomes that can occur with different probabilities. And so you have the outcomes, the sort of payoffs that you have, and you have the probabilities that are associated with those. And then that defines a space of pairs of gambles, right? Each of those things is a dimension of that space. And what you're trying to do is learn a function that maps you from this configuration of outcomes and probabilities to the probability that somebody chooses, say, option A. Right? And that's just a very natural sort of machine learning problem. And so if you think about this as a machine learning problem, that makes sense. The big difficulty, though, is that the amount of data that you have for estimating that function is very small. And so the question is, how can you try and solve this problem in a way that allows you to do a good job of estimating that function despite having very limited data? And so we came up with a way of solving that problem, which we called theory-based pre-training. But the basic idea is that even though you've got a very small amount of actual human data, you do have that 100 years of history of psychologists trying to predict the kinds of things that people do. And in particular for this kind of task, we actually have pretty good models of the kinds of things that people do when they make decisions. And so you could take those theoretical models that psychologists have developed and then generate a whole bunch more data from that theoretical model and then use those data to pre-train your model, right? So now this is something that people do in robotics. It's called sim to real, right? So you train your robotics, your system which is going to solve a robotics problem in a simulated environment, and then you transfer it to the real environment, and then that's a way of getting around the problem that, you know, in robotics is very analogous to the problem you have here, that getting data from the real world is expensive, right? And you can sort of simulate data much more easily. So you can simulate lots of data, train the model on the simulated data, and then transfer to that real world setting. So it's exactly the same idea, it's sim to real, but here the sim comes from our psychological theory, and then the real is the actual decisions that people make. And so in this case, we could take a theory that people had come up with. That theory was, in fact, the theory that did best in the 2015 choice prediction competition. It's a pretty complicated psychological theory. It says there are 4 kinds of heuristics that people use, and they use them in different circumstances and so on. But despite the complexity of that theory, what it allows you to do is generate data. You can say, what would people do on this particular task? Generate a bunch of data from that, use that to pre-train, say, a neural network model. So you're training that neural network on data which is generated from that psychological theory. Then you've got your little bit of real human data, and you just use that at the end to sort of fine-tune the results. And what we found was that just doing that was actually sufficient to allow us to do extremely well in generating these predictions. So it might be a little hard to see here, but so this is comparing our approach, which is just a neural network, a multi-layer perceptron with this cognitive prior, to all of the different kinds of models that were used on the choice prediction competition 2015 data. And then this is showing it on the 2018 data. We actually won the 2018 competition, but slightly embarrassingly, my graduate student submitted the wrong model. So they submitted our backup model. Our backup model was good enough that it actually won, although it didn't use this technique. And in fact, if he'd submitted the right one, we would have done even better, right? So, so this kind of approach, though, is something that worked really well for at least being able to make progress in this setting where you have this very limited amount of human data. And the idea is start with the theory that you have. Even if that theory is not perfect, it's closer to the right answer than wherever your neural network normally starts off, which is some random place in weight space. And so pre-training moves you towards a solution, which is basically instantiating the idea which is in that psychological theory, and then training on a little bit more data moves you away from that and towards the actual human responses. Okay, so this is thing number 1, right? Method number 1, theory-based pre-training. We generate simulated data from a theory. We use that to train a model, and then we can fine-tune away from it. But the more fundamental problem here is just that if you wanted to use machine learning methods to try and make sense of these decision data, you just did not have enough data, right? So a lot of these machine learning methods work most effectively when they have more data. And so as a consequence of having this experience and sort of saying, you know, we kind of worked out from generating that simulated data how much data you'd actually need in order to train a neural network well. And so the next thing we did was actually just go off and collect those data. So in the last 10 years or so, there's been a revolution in the kinds of methods that are used in psychology where it's possible for us to go online and basically turn dollars into data using crowdsourcing services like Amazon Mechanical Turk. So that's what we did. So I had told you that this large data set that was previously used in the choice prediction competition consisted of 300 pairs of gambles. What we did was actually go off and then we collected data for 13,000 pairs of gambles. And so that's a sort of 2 order of magnitude increase in the amount of data that we have in this kind of task. And by doing that, we're able to just sort of cover the space of these problems in a much more comprehensive way. So just to get a sense of what that looks like, this is a visualization of the data set that we collected. This is a 2-dimensional projection of that high-dimensional space that we're trying to learn a function over, where this is extracted from the internal representation of one of the neural network models that I'll show you in a minute. But it just sort of gives you a sense of what this looks like, so the layout of so each of these dots corresponds to one of those choice problems, a choice between a pair of gambles. The green X's correspond to sort of historically important pairs of gambles. So in the development of theories of choice, going back over the last 50 years or so, These are the sort of things that psychologists came up with as points in the space that were meaningful for discriminating between one theory or another. The red dots correspond to the 2018 choice prediction competition, and then the black dots correspond to the data that we collected. And so what you should be able to see is there's a lot of black dots, there's not a lot of green crosses, there's not a lot of red dots, and those black dots are sort of filling in parts of the space that really weren't represented in the previous data. And so what this means is that now we have this broad base of data from which we can try and estimate this function that tells us what's the probability that people select a particular option. And so there's another thing to say about this, which is just, this really represents a very different kind of method from the kind of method that psychologists have previously used for trying to make sense of human behavior. So for a long time, collecting data was expensive and difficult. You had to get people to come into the lab to get data from them. And that limited the kinds of experiments that people would run. So as a consequence, the way that psychology has been done for those 100 years is people sort of come up with a hypothesis. They might have an alternative that they're comparing it to. They design the perfect experiment to distinguish between those hypotheses, and then they run that experiment, and then they report the results. And what that does is essentially, if you kind of think about what this is doing, it's kind of like jumping you around those green X's in this space as you're going from one theory to another. But it's not allowing you to get a comprehensive picture of what that whole space looks like, right? Of how it is that people's decision-making varies across all of those different kinds of problems. And so by going out and just sort of collecting this entire space of what these possible choice problems look like, we're able to collect that much more data that we can get a comprehensive picture of what the whole space of possibilities is, and then we can look at how the kinds of decisions that people make might vary across that space. And the way that we do that is by using a method that we call differentiable theories. And published in this paper called Using Large-Scale Experiments in Machine Learning to Discover Theories of Human Decision-Making. And the authors here, I should have said on the previous project, it's the same set of authors, Josh Peterson, David Borjan, Mayank Agrawal, Daniel Reichman. So the idea here was that if we think about this problem in terms of trying to estimate this function, which relates choice problems to the probability that people select a particular option, we can then characterize what that space of functions looks like as well. And I'll explain this more in a moment, but the basic idea is that we can express the kinds of theories that have previously been talked about as theories of human decision-making in terms of a hierarchy of functions, and then we can explore in that hierarchy of functions where we can find functions that actually correspond to good solutions to this problem. And the tool that we're going to use to do that exploration is the kind of tool that drives a lot of modern machine learning, which is that if you can express a theory in a form which corresponds to a differentiable function, then you can use tools for automatic differentiation to then automatically search over the space of functions to find the one that best corresponds to the data that you have. And so that might sound a little weird and complicated, but it's exactly the procedure which is used in sort of backpropagation algorithms that are used to train deep learning models. What we're doing is taking our theories, expressing those theories in terms of what's called a computation graph that describes how it is that these functions are composed out of simpler parts. And then as long as those parts are themselves differentiable, we can use these tools of automatic differentiation to then allow us to use gradient descent to explore the space of functions and find what function in that space best corresponds to something which is going to capture people's behavior. And so what this allows us to do is exhaustively evaluate models that might belong to different classes. And so now we can define a constraint which corresponds to what class of theories we're thinking about, and then we can find the very best model in that class, and then that allows us to sort of evaluate how the constraints that correspond to those classes actually translate into making a difference in predicting behavior. And so the kinds of classes of models that we looked at, things that corresponded to classic kinds of choice models, but also things that were more general than that. So one starting point is expected utility theory. And the way that we express this here is with the idea that the probability that you choose one of those gambles, say option A, hoping the lights come back on. It wasn't me. Okay. It's probably someone in the back of the room is probably leaning on a light switch. But, is going to be proportional to something which reflects, this is just the sum of the probabilities of those outcomes and then the utility which is associated with those outcomes. So in here, you have this utility, which is like how much value you would assign to getting some number of points or some number of dollars. And the classic idea here is that this utility function is something that, say, is a saturating curve, right? Sort of like decreasing in the rate at which it's going up over time. And this allows you to capture the fact that essentially, they say your first $1 million is the hardest, but it's also probably the $1 million that you value the most. The next $1 million you make after that, you might value less than the first million, right? So as you get more money, getting more money is sort of has decreasing value to you. But this function, normally the way that you might try and estimate this function is by defining some class of utility functions and trying to find the thing that's in that class of utility functions that best fits the data. But what we can do is to say, well, in fact, let's leave that class unspecified, and instead we're going to fit a neural network, and that neural network is going to play the role of capturing that utility function. So this is a completely non-parametric, completely flexible way of allowing us to estimate what that utility function is from the data which we collect in these decision problems. And so then what we can do is we can say, using this neural network to represent the class of functions that we're estimating, try and find the best function in that class, and that's going to give us our sort of best version of this expected utility theory model. The next sort of level of complexity, right, in terms of moving up through this hierarchy of models is one that says, okay, yes, you're allowed to assign different utilities to different outcomes, but let's also say that you subjectively transform the probabilities that you associate with those outcomes. And this is a model that's called prospect theory. It's very famous. It's the source of Daniel Kahneman's Nobel Prize. And the basic idea here is that there are two things that go into this. So one is that the way in which we're going to define this utility function is now sensitive to whether you're experiencing losses or gains. And so that allows you to capture the fact that, say, people might make different decisions if they're given a choice between, say, an 80% chance of winning $4,000 or a 100% chance of winning $3,000. People often choose the 100% chance of winning $3,000, right? The sure thing is attractive in that situation. Whereas if you're given, say, an 80% chance of losing $4,000 and a 100% chance of losing $3,000, most people choose the 80% chance of losing $4,000 because there's a chance that you could get away with it. And so that asymmetry is something that you can capture by allowing to have an asymmetry in that utility function. Whereas if you are interested in capturing phenomena like, for example, the fact that people are willing to play lotteries, right? So where, say, you might be willing to pay $5 for or you might be willing to trade off a 1 in 1,000 chance of winning $5,000 for a 100% chance of winning $5, right? The trade-off between those things might seem reasonable. You can capture that through the fact that people might overweight small probabilities, and as a consequence, overestimate the value of gambles that involve gains associated with those small probabilities, and then underweight larger probabilities. And so those kinds of deviations from expected utility theory are the kinds of things that motivated studying particular choice problems, but there are also things that correspond to different choices for the forms of these functions. And in the same way, we can use a neural network to capture the forms of these different functions, and then try and find what's the best corresponding sort of version of prospect theory for capturing what's in the data. And then the two last classes of models that I'm going to talk about are a model we call a value-based choice model, which just says you're going to assign a value to each gamble based on the probabilities and the outcomes that are associated with that gamble. But we're going to allow the form of the function that translates probabilities and outcomes into those values to be completely free, and we're going to fit that with a neural network. And then what we call context-dependent choice, which just says you're going to take all the probabilities and outcomes and you're going to put them together and smush them into one big function, and then that function is going to give you a probability that you make a particular choice. And so again, the key point here is that as we go through these models, we're sort of introducing more ways in which these models are free, right? So they sort of form a nested hierarchy of models, and we can find within each of those classes of models the best fitting model by using these kinds of tools of automatic differentiation and then optimization through gradient descent. And so when we do that, we can ask questions about how well human psychologists have done and economists have done in exploring this space of choices. So for example, we can take expected utility theory, right, and take something that has the functional form of expected utility theory. And then what I'm doing here is showing this is how well we do in fitting the data, right? So this is a smaller number here is better. And then this is showing how much of the data set is a model is trained on. And then all of these gray lines correspond to different hypotheses that human researchers had come up with for what the form of that utility function might be, and then taking that form and then estimating it from the data. And the blue line shows what happens when we train our very constrained neural network that's trying to freely estimate the form of that utility function. And so what you can see is that humans have done pretty well, right? Humans have actually come up with pretty good characterizations of what the form of that utility function might be. There's some of these gray lines that are quite low here. But then, and then as we train our neural network model on an increasing amount of our data set, it can sort of discover a function that corresponds to the thing that's the best in the set of functions that human beings have come up with. So humans have discovered, like a pretty good characterization of these kinds of models. This is what ends up being estimated from that procedure. And you can do the same thing for prospect theory, so this is showing the same thing. Here, again, all of these gray lines correspond to human proposals about what the form of that probability weighting and utility function might be like. And then one interesting thing that you can see here is that as we train our prospect theory model, it sort of quite quickly does better. And then this is another version of prospect theory called cumulative prospect theory, which does even better with relatively small amounts of data. So again, we're able to sort of rediscover the kinds of things that it's worth saying, took psychologists and economists working pretty hard for 50 years, doing lots of experiments and theorizing pretty hard. We can rediscover those in a single experiment where we went out, collected a huge amount of data, and then used these constrained neural networks to search through the space of those functions. And again, this is what this looks like. This probability weighting function doesn't look quite like the one that people normally assume for prospect theory, and I'll come back and talk about that a little bit later on. Okay, so now this is what happens if we take all of those classes of models that I was telling you about before, and we start to compare them against one another. So here, the red and blue lines, these are the ones that correspond to those classic models I was telling you about on the previous slide, expected utility theory, prospect theory, and so on. This light blue line is what happens when we use the value-based model. So this is the model that assumes that people assign a value to each gamble based on its payoffs and probabilities and so on. And that, if you get enough data, right, so when you get to about 30% of the way through our data set or 40%, that starts to be able to beat these sort of best human theories from history. The dashed line here corresponds to the best human theory from the choice prediction competition, and the best theory in all of the theories we looked at. We looked at about 30 different theories that have been proposed by psychologists and economists. This performed best in predicting the data, and it performs even slightly better than this value-based model. But if you have a completely unconstrained neural network that's just trying to predict the probability that people make a choice, right, once you get past 30% of the data set or so, that starts to outperform this best model that human beings have come up with. Okay? So the key takeaway here is that by the time you get to the end of the data set, there's quite a large gap between what the neural network model that's just completely unconstrained is trying to learn from the data can do in terms of performance and the best theory that humans had come up with in terms of being able to make predictions about these kinds of decision problems. And when we look at that gap, that's something that we can see as an opportunity, right? That's an opportunity to actually realize that there are things that we didn't know, that we have an opportunity to now learn as we try and make sense of these data. The other thing I want to point out here is this is that choice prediction competition from 2018, the previous largest data set, right? And if you look here, you get a conclusion which is very consistent with the kind of conclusion they had, which is, those sorts of psychological theories do a good job, right? And they're better than the, completely flexible machine learning theory. So this is only something which emerges once you have enough data. But once you have enough data, then the more flexible story, ends up being able to get this performance. Just for people who are worried about overfitting, all of this evaluation of mean squared error is done on held out data. So this is a validation mean squared error. Okay, so let's talk about, this is an opportunity, right? It says that there's something which we're missing in trying to account for human decisions. It's not in the psychological theories that we have. It's also a problem, right? And the problem is that this model that I just described to you consisted of us just taking a neural network, throwing it at the data, and then learning something from it, and we have no idea what it learned. Okay? So we need to solve that problem in order to make the most of that opportunity. We need to try and figure out what this is doing in order to be able to actually learn something about explaining human decisions. So in order to do that, I'm going to switch gears. I'm going to talk about another method for trying to use machine learning models to understand human behavior. This is something we call scientific regret minimization for reasons that I'll explain in a moment. It's kind of a joke for people who are used to the idea of regret minimization in machine learning. But the idea here is essentially that when we have a really well-performing black box model, like this neural network model, we don't understand what it's doing, it can still nonetheless be useful in guiding us in theory development. And the idea is that we can use that black box model to critique an interpretable model. And the way that we make progress is that we look at the errors that we could have predicted. The black box model tells us we could have predicted, and use those to critique the model that we work with. So just to illustrate how this works, I'm going to return to another example which is motivated by this case. This is a huge data set of moral decisions that was collected by the Moral Machine Project. So they had, in the part of the data set that we're looking at, about 10 million decisions that all involved a task where people had to say, you have a car, this is a self-driving car, you can see there's no one in the car, that is headed towards an intersection. It's a version of the trolley problem. The car is going to hit somebody on the intersection. It's either going to hit this side or this side. You have to make a decision, should the car continue to go straight or should it swerve, in which case it's going to, if it continues to go straight, it's going to kill these people. If it curves, it kills these people. It's a horrid, sort of morbid example. It's exactly the kind of thing that you might want to know if you were trying to design self-driving cars. This is the way that they motivated it. You wanted to design self-driving cars that would capture human moral intuitions. But for our purposes, it just consists of a very rich and complex data set for which they had a huge amount of data, where we can actually see if we can actually use some of these methods to try and make sense of the decisions that people make. So in this case, there's about 20 different kinds of people who can appear on different sides of the road. The number of them can vary as well. So you can think about representing each of these scenarios just by the number of those different people who appear on the road, right? And again, we have a problem where we have a vector, right? Now we have this vector of how many people are on the left-hand side of different types, how many people on the right-hand side of different types, that we're trying to map to a probability where that probability is now either go straight or swerve the car. You can make a very principled cognitive model, a sort of rational choice model, which just says you assign some utilities to each of those lives. Those utilities might vary based on the type of individual that's represented. And we're going to add up those utilities, and then you're going to make a decision about which side you want to go to just based on the sum of those utilities, right? And so it's the relative utility of the left side versus the relative utility of the right side. And then you can make that model a little more complicated by adding in what moral philosophers might call deontological principles. So for example, you might think that somebody who's crossing the road legally has a privileged value compared to somebody who's crossing the road illegally. So you might prefer to avoid hitting people who are crossing the road legally and in favor of people who are crossing the road illegally. Or one thing that's very clear from the psychological data is that in these kinds of situations, people prefer inaction to action, right? They're sort of, taking an action seems like it's more morally laden, and so as a consequence, you might have a preference not to swerve the car at all, and in fact, that shows up in the data. So these are things that you could just add in as extra sort of constants that you add into this equation, where they're features that correspond to whether the scenario, corresponds to satisfies this particular rule. And then we can contrast this kind of model with a black box model, in this case, again, in a sort of neural network model that's just mapping that vector into a probability. Again, what you find is that machine learning does better than the psychologists, right? So here, this is increasing the size of this data set. So I told you it goes up to about 10 million decisions. And then these different lines correspond to, this is now I'm showing you the accuracy of the model. So here, higher is better. And these different lines correspond to different models of the kind that I was talking about before. So the blue line is if you give equal weight to all of the lives involved, that does sort of okay. You can make that better by distinguishing between animals and people. So if you have different weights for animals and people, you get a little bit better. You can do better than that by having one where you have different values for all of those 20 different kinds of individuals. And then if you add in those extra deontological principles I was telling you about, you can get to this red line here. But then, if you get enough data, the neural network ends up doing better, right? And is outperforming the best psychological model here. And so one thing you might then want to do is to say, let's see if we can figure out what the psychological model is missing. And a standard technique that you use for doing that is something called error analysis or residual analysis, where you might look at the residuals from the model, the things that it fails to get correct. And so if we do that, and we compare our best sort of theoretically motivated choice model with the neural network model, what you find is this, right? So this is now, I'm showing you the case where the error between our choice model and the data is largest, and it corresponds to this situation. It might be a little bit hard to see. There's a bunch of people on the left-hand side of the road. There's a bunch of cats on the right-hand side of the road. and the data says that 99.4% of people chose to kill the people rather than the cats. And so we have no idea what happened there, right? And the people who made the data set have no idea what happened there. But if you collect 10 million data points, this is the kind of thing that sometimes happens, which is that the more data you have, the more opportunity there is for weird outliers to happen, right? And if you're comparing your residuals to the data, and you've got huge amounts of data, the biggest residuals you're going to find are going to be these really weird cases where something went wrong. And so doing that kind of analysis based on residuals is not particularly effective in these kinds of massive data sets. And so that motivated us to think about this approach we call scientific regret minimization, which is that you should only be concerned about the errors that could have been predicted, right? So if you go back to this and we look at the choice model here says, no, that shouldn't happen, right? The neural network also says that shouldn't happen. And that should tell you that this is a case where, despite the choice model being different from the data, maybe you don't actually care so much. Because the model that we've made using the neural network, which is kind of like the best model that we've come up with, still doesn't do any better in that circumstance. And as a consequence, this is an error that is maybe less important than it seems like. And so this is the idea then, right? The regrets that we're minimizing, we should only regret those things that we could have done better, right? And this is a situation where whether we could have done better is told to us by that neural network model, our sort of black box model, which is the best predictive model we have. And so the idea is we fit a black box machine learning model, we evaluate residuals to that model, not to the data. And if you're a social scientist or any kind of data scientist, now you're kind of freaking out because you're like, I'm just told you that what you should do is throw away your data, don't care about the data, just compare it to that model, right? It's a very sort of unfamiliar and uncomfortable thing to do. But it turns out that in this situation, if you have enough data, training a black box model, fitting it to the data, and comparing residuals to the black box model instead of the data works better, and I'll show you this in a moment, because intuitively what happens is that the model becomes a smooth version of the data and thus a better target for critiquing the data, right? And so just to sort of show you what this means, here's a sort of simulated example, right, where the black line corresponds to a true function, which we can know because we're simulating data. The gray dots correspond to data that are generated from that function. And the blue line is our sort of is our neural network prediction. And so now imagine we're trying to fit some function to this, and we're trying to figure out what model is the best model of these data. We have a nice theoretically interpretable model that we're trying to fit. And I told you it's okay for us to do this evaluation relative to the blue model rather than to the data points. And the idea is that, in fact, what's happened when we've got enough data is now the blue model is closer to the true function. So if you are comparing the residuals relative to the data points, these big outlying data points are going to be the things that are going to drive your residual analysis. And if you compare it to the blue function, you're actually going to do a better job. And you can actually express that in terms of math. I'm not going to explain the math, but for people who like math, the basic idea here is that we can think about decomposing the sources of variance that are going into those residuals, right? So in this case, f of x is the true function, g of x is our estimated, this is our nice theoretical model. And so in one case, we have the true function plus noise, right? That's what you get when you compare to the data. And you end up with something which reflects how well your theoretical model fits the true function, and then a term that reflects the noise in the data. But if what you did instead was compare the residual between your theoretical model and your black box model, which you fit to that function, f of x, you can work out what you get is a term which is the difference between f of x and your theoretical model. But you also get this other term which reflects essentially how well your black box model fits the true function, and then how correlated the errors might be between your black box model and your theoretical model. And if you get enough data, this can be driven so that it's smaller than the noise variance. And so this makes a prediction that as you get more data, there's going to be a point where the residuals between the true model and the data are, sorry, the correlation between the residuals to the data is less than the correlation between the residuals to the black box model, and we find exactly that transition, where if you get enough data, your residuals to the black box model are a better predictor of your residuals to the true function than the residuals to the data are a predictor of the residuals to the true function. Okay, that was a little complicated, but we got there. Okay, so, and that's exactly what happens. So as you do better in fitting the data, that's what the right plot shows, you get to this point where you have this transition, and in fact, it's better to critique your model against the black box model. Okay, so let's go back and now look at this in the context of our problem. So if instead of looking at the biggest residual to the data, we look at the biggest residual to the neural network, this is the case which is the biggest residual to the neural network. If you look at this, we have, again, it's a little hard to see, there's a human on this side and a cat on this side, and the human is crossing illegally and the cat is crossing legally. And our choice model says you should kill the human because they're crossing illegally, right? And the neural network model says nope, right? And the humans say nope, right? And so what's going on is that our model which said, oh, you should favor legal crossers is a little bit wrong. And in fact, you should, if you have a choice between killing a human and killing an animal, you should probably, I'm not going to interpret this as a moral prescription, but people find it more permissible to kill the animal than killing the human. Okay, so that's a really easy feature that we can put into our model, which says look for these situations and avoid them. You can then, do this again and again and again. It's a kind of abductive loop, right? So now we can do this again. On the left-hand side, this is, again, the biggest residuals to the data, which are not very helpful. On the right-hand side, this is the biggest residuals to the model. And now that we've added in that extra feature, it now catches a bunch of these cases where we have, this is cats crossing illegally, humans on this side. This is kids crossing illegally, adults on this side. Basically, what these errors show is that the designation of an illegal crosser should not be applied to cats and children, right? So animals and children are not sort of aware of whether they're crossing legally or illegally, so they shouldn't be penalized for it. And so that's another feature we can put into the model. This is another, next iteration, what we find is that the prescription that you should choose that it's more permissible to kill animals than humans does not apply when those humans are bank robbers, right? So we need to have an extra sort of recognition that that's a deviation that we allow, and then we keep on iterating, right? So now we discover that pregnant women have an extra bonus that was not reflected in the bonuses we had in the model. There's actually a sort of very sharp deontological rule about it, and so you can add that into the model and so on. And each of these iterations, you're discovering something kind of interesting about human moral decision making. You can do that for a long time. So the final model looks like this, right? There's lots and lots of features that come out of that. We then did a whole bunch of extra experiments where we went back and we said, we found these things. Are these things real? We ran new experiments. We validated that those things were real. But the point here is that taking this data set, which had 10 million human decisions in it, using this procedure where we're critiquing against our black box model, it's kind of like the equivalent of doing it's like 70 papers that could have been written where that paper is about each of those distinctions that I was showing you in each of those iterations. It's just it was all done in one giant data set, and then you needed to have this kind of data analysis method to pull all of those pieces out. And so there's a lot of weird, interesting things that we learned about human moral decisions. You find these weird higher order effects. The first order effect, crossing illegally increases the risk of being hit. The second order effect, unless crosses are children, right? I showed you that one. There's a third order effect, which is that unless those children are with an adult, in which case they get back to caring about illegality. And then you also find these weird unexpected interactions. So if you are a woman, then if you are crossing the road and it's unknown whether you're crossing legally or illegally, right? If you're jaywalking or not, the rate at which it's sort of considered acceptable to be hit in that circumstance is close to the average of legal and illegal. But if you're a man, it is close to illegal, right? And so this is saying men are not given the benefit of the doubt in a circumstance where the illegality of their actions is unclear. Okay, so these are not things that you necessarily want to build into your self-driving car, but they are things that it's helpful for us to know about human moral decision making, and we're able to discover them using this kind of procedure. Okay. So I'm now going to go back to risky choice and sort of try and land this plane, right? So now we have a method that we can use for trying to figure out what's going on in that black box model. And when we did this, what we did was we took that neural network that I showed you, and we took a prospect theory model, and we said, what is the neural network captured that's not captured in prospect theory? And we found that basically those phenomena that I showed you earlier on are not consistent across the entire space of problems. So those phenomena of loss aversion and of probability, giving greater weight to small probabilities, classic phenomena which motivated prospect theory definitely show up in the space of decision problems, but they're not uniform across that space. We can capture that by defining what we call a mixture of theories model. And the way that this works, it says basically, let's assume two different kinds of utility functions, and we can, again, estimate these from data, and two different kinds of probability weighting functions, where one of those is constrained to be perfectly linear, and the other is allowed to be free. And then what we're going to do is for every problem in our decision space, we're going to learn a function which is not from the problem to the probability that somebody chooses one option or another, but it's a function from the problem to which of these utility functions do you use and which of these probability weighting functions do you use. So like how sensitive are you to loss aversion? How sensitive are you to small probabilities? When we do that, what we find is, as I said, you kind of find that these things are sort of not evenly distributed across the space. So this is showing you, again, the space of choice problems. So here, more yellow is less probability, this sort of linear probability weighting function. More red is this more curvy, classic probability weighting function. Here, more green is this sort of classic loss aversion utility function. More purple is this sharper and more symmetric loss function. And basically, you can go in and you can figure out in the data what's going on. But basically, they correspond to, you don't see this kind of probability weighting for problems where those probabilities are sort of like in the middle here. So it does affect the small probabilities more, but it doesn't affect them so much in the middle. And then for loss aversion, when you have problems which are close to being dominated, so where it's close to it's sort of one option being strictly better than the other, people just sort of hone in on those math differences, right? Where just like one thing being slightly better than another is enough to push them in that direction. And so as a consequence, you get this very sharp and symmetric utility function. And you can use the same kind of model to explore individual differences where you can say, it turns out when we look at our data with another data set that we collected, individuals vary in the extent to which they use these different ways of making sense of the data. Sorry, making sense of their choices. Okay. So this approach that I've talked about is in many ways a sort of general paradigm that's now being applied by us and by other people in a lot of different settings, right? And that paradigm is collect a large data set, optimize theory, constraint, and black box models, and then iteratively critique the models against the black box to try and figure out what it is that you're missing. And so we use this. This is in the context of this risky choice setting, but we've also recently used this in the context of 2x2 games of the kind sort of studied by classical game theory, where we're able to use this kind of approach to actually understand things about how much people iterate when they're trying to make sense of the play of their opponents, and how that's modulated by the complexity of the task that they're performing. And it's also been applied to things like spatial working memory, planning, and this is a cool recent paper that looks about how this might apply in the context of reinforcement learning. And the effectiveness of the approach increases with bigger and better black boxes. So as we're able to sort of leverage these machine learning tools, they can be used to get insight into exactly how it is that we might want to impose constraints and the kinds of principles that we might want to use in explaining human behavior. Okay. So those are three methods for combining theory and data. Method 1, theory-based pre-training. Method 2, differentiable theories. Method 3, scientific regret minimization. I promised to tell you how we can create systems that have good inductive biases for understanding and predicting human behavior. And the kind of approach that I just outlined is a way to do that, right? It's a way to come up with better theories that then you can feed back into the system as a way of generating things like synthetic data that you can use for pre-training, such that you can create models that instantiate strong inductive biases. And in some other recent work I'm not going to have the time to talk about, we've generalized that to something we call inductive bias distillation, which uses more sophisticated machine learning methods like meta-learning to take an inductive bias from a probabilistic model, like a sort of Bayesian prior distribution, and then transfer it into a neural network. And that expands the space of kinds of theories that we're able to translate into inductive biases in this way. But one question that you might have is how this kind of inductive bias compares to the inductive biases of the kinds of AI systems that are making the news lately. So large language models like ChatGPT or Claude or Llama or Gemini, these models have some kind of inductive bias that they've learned from the training data they've been exposed to. And very briefly, we've sort of looked at this. I'll tell you this is a story in 4 papers extremely quickly here. So first of all, if you take large language models off the shelf and use them to try and predict the kind of choice data that I was showing you, they are not great at it. And the way in which they're not great is that they, as the title says, assume people are more rational than we really are, right? So off-the-shelf models do some kind of mixture of just doing weird stuff and calculating expected value for the gambles, right? So calculating just like what the probabilities times the utilities are and sort of adding those up and just saying, okay, choose the one that has greatest value. That's an entirely rational thing to do. It's not the thing that people do, as reflected in the data I showed you before, but it's the thing that the models assume that people do. And consistent with this, we showed in another paper that if you just take the equivalent of these kinds of large language models, train them on a data set which corresponds to arithmetic, right? In this case, the arithmetic that you use for expected value computations, you get exactly the same score in predicting people's choices that you do if you take these models that have been trained on massive, linguistic corpora. One funny thing that came out of this first paper here, so first of all, using chain of thought or other kinds of, this sort of inference time compute methods that improve performance on many kinds of tasks, that does not work well. In fact, it makes the models assume that people are even more rational, right? And that's consistent with the fact that it enables this kind of math-based, reasoning-based computation. It strengthens the correspondence with expected value theory. The prompt intervention that we found that had the biggest effect in producing something that was more like human behavior was to tell a large language model it was not predicting a human, but it was predicting the choices of a monkey. So you can make of that what you will. The other thing is that fine-tuning helps. So in a nice paper by Marcel Binz and Eric Schulz, they showed that you can take these off-the-shelf models and then fine-tune them on these kinds of data, holding out data in the way that we did in those previous analyses. And then they can actually do better, and they can get closer to the kinds of models that I was showing you before. That principle is instantiated in a paper that we collaborated with them on, where they fine-tuned a large language model on a massive amount of psychological data. So this is psychological data from a bunch of different kinds of tasks, and then evaluated performance there. And so what you see when you do that, this is here all of the different tasks that were used from these psychological experiments. The sort of light gray lines correspond to sort of standard cognitive models. The pink lines correspond to off-the-shelf llama, and then the purple lines correspond to this model, which they called the centaur model, because it's humans plus a llama. I guess somehow if you put those together in the right way, you get a centaur. And it actually does result in a significant improvement in performance. And so these kinds of models are interesting. They're not explanatory models, but they're powerful predictive models, and it's something that you can use in the context of some of the methods that I was talking about before. So you can use this as the basis for critiquing a theoretical model, right, doing that scientific regret minimization procedure. And the nice thing about these fine-tuned large language models is you can do that for arbitrary tasks, right? So now you can give it a new psychological task you've run. You can compare it to your data. You've got a theoretical model that you'd like to critique. You can critique it against the predictions that come out of the centaur model, and that gives you a tool to do this kind of theory iteration. Okay, so conclusions. So first of all, psychological theory can be used to create models with good inductive biases for predicting human behavior, right? And some of the methods that I talked about, theory-based pre-training, differentiable decision theories, are cases where we're using psychological theories in different ways to constrain those models. Second, machine learning can be used to guide the development of better explanations for that behavior through things like scientific regret minimization, although they might end up being more complicated than we expect, right? And so remember when I showed you the result of following that procedure for the moral reasoning case, it was like 70 different factors that it identified. As we get more data, having machine learning models is very helpful for allowing us to make sense of those data, but it also reveals some of the intrinsic complexity of human behavior. And one of the things that we need to get comfortable with as scientists as we start to work with these larger data sets is that the kind of simple explanations that we might desire for intrinsically complicated things like human behavior might not, in fact, be the things that come out of those analyses. So, thank you very much. I think so. If you want to ask questions, there's microphones. There's one here, and there's one over here.
Testing, testing.
Yeah.
Hi. I have a question about the regret minimization. So you showed that there's this crossover point at which point using the model instead becomes useful. For a new setting, is there a diagnostic to know whether or not we've crossed that threshold?
Yeah, so it relies on you having an estimate of what the noise is in your data, right? So the crossover point is determined by the point at which the error of your predictive method falls below the expected noise threshold. Yeah.
Hey, Tom. Thanks for the really inspiring talk. So the theories that are produced by these methods will be theories of human beings under certain sampling assumptions about where the data come from, that you've got a random sample of humans and that there's random variation in humans' preferences or their cognition. Those aren't true, right? And so I wonder how you've thought through the problem of biased sampling in the data sets and then meaningful variation amongst the human beings.
Yeah, so in this case, we're working with the kinds of data that we can get, right? And in particular, kinds of data that we can get at scale. So we're definitely constrained by that. We see some of that already in, even if you look at differences between online and lab samples. So one of the things on this slide, where I showed you the performance of the best human model, this model was calibrated on lab data. And if you calibrate it to our data, it does a little bit better, right? And so that's something which matters. The other thing I showed you briefly was being able to capture individual differences, right? And I think this is a way that you can start to think about that variation, is that once you have constrained models, at least of some population, you can make models of individuals within that population, and you can think about how the distributions of individuals vary across populations. So there's no way to answer those questions without being able to collect data from a wider range of populations. And these sorts of online data collection tools are starting to increase in the range of populations that you can sample from. Now we have a collaborator who has data from about 60 different countries where we can look at that variation, but that's obviously a really important thing to think about.
Thank you.
Just want to broaden that a bit. The generalizability of your answers may be very dependent on your data set. For example, if you ask the same questions to cat lovers, you may have gotten very different answers on their choices. So that's a caveat in all the extrapolations. They only apply to people who made up the data set.
Yep.
Second question has to do with prompt questioning. That could bias many of the foundation model answers. They are very reluctant, for example, to criticize your question. So if I ask the question, am I right on this? They will hedge and never say, or very seldom say, I'm wrong. So the prompting has a lot to do with the type of answers you get, and I wondered if you've taken that into consideration.
Yeah, so on the first question, one nice thing about the moral machine data set is that they have a lot of information about what the sources were for the data. And in particular, you can look at things like variation by country as well as variation by demographic groups. We made a model where we tried to look at those kinds of individual difference variation in that data set. And all the ways that we tried it, we weren't able to find an improvement in performance as a consequence of doing that. Which doesn't mean that those effects aren't there. It just means that they weren't things that we were able to detect at a scale that meant that they made a difference in prediction performance. For the second question, yeah, so for the results that I told you about here, we tried a range of different prompts, and we see very similar results. We ran this, the three main ways that we were concerned about were what would you do question, what would you predict a human would do, and a kind of like simulate a human question, which corresponded to at least three different kinds of settings in which large language models are used. And across those three different settings, we found very similar performance. Yeah. So we also tried doing different demographic prompting in that setting as well. Yeah.
Professor, thank you so much for coming. My name is Bessie, and I'm currently a student here, and I study computer science. So most of today's talk kind of focused around human decision-making on individual basis. And I was listening to your talk, I was thinking, another thing that we do on a daily basis is we do collective decision-making and we do collective thinking. So I was wondering if you have any thoughts on how, techniques might change, or you've done any research experiments on when models are acting as agents where their priors are different, but through discussion, debating, they have to change that prior and reach like a unanimous or like some sort of a uniform posterior at the end for a good output. I was just curious if you had any thoughts on that.
Yeah, so we've done a bunch of work on like different kinds of processes of cultural evolution. So in that setting, most of the questions that we've been focused on are more how can you create circumstances where people are actually able to improve over time, right? So if you have a community that's trying to figure out how something works or trying to come up with good algorithms for solving a problem, what are the mechanisms that make it possible to do that? We've got a few papers where we've actually run some of these large-scale experiments that explore that. One of the things that's effective for doing that is just being able to see not just what somebody else did, but how well they did as a consequence of that, which supports a kind of social selection effect. And then we currently have a collaboration with some folks where we're trying to do some work where we're looking at AI-mediated interactions and how that's something which can help support people finding better solutions in those settings too.
Awesome. Thank you so much.
Yeah, just wondering whether you have any plans to investigate the prediction from the game theory. Some of them is too relational, you know?
Yeah, so I briefly mentioned the game theory case. So I can just show you a picture. So what we did in that setting was very similar kind of approach where we can take a two-player game. You can think about this as now our sort of vector space corresponds to the payoffs that are associated with each of these options for the two players, right? So now we're mapping this vector into a space, which is what's the probability that we just focus on the row player, that the row player makes choice of option A. And so we can think about that now as a problem of we want to map that space to a probability in the same way. We can define sort of meaningful classes of problems. We collected a massive data set of 2,416 matrix games that were distributed across these different classes of games. And then in this setting, one of the key scientific questions is about how much, they're called like level K models, right? Like how much people think about what the move is that the other person's going to make in selecting their move. And a lot of the debate had been about, do people do this one step or do they do it two steps? Or, like sort of framing this problem in a very dichotomous way, in the same way that in the simple risky choice case, it was, is it this theory or is it that theory? In that case, we showed it's kind of both, right? It's like this is something which varies across the space. It's not which theory is right, it's where are these theories right? And we did the same thing in this two-player game setting, where what we're able to show is that the degree to which people iterate varies by problem. And we can construct a very straightforward predictor of that variation, which is based on a sort of, we start off with a black box model, but we're able to pull out interpretable features that correspond to essentially the complexity of the game. And you can quantify that in terms of things that correspond to like the number of equilibria and things like that. So, yeah.
Thank you so much for a wonderful talk. And I have some question regarding some of the learnings you went through while training the models or creating the prompts, because we have a mental wellness startup, Happiness Factors, where we are just trying to train the models for the mental wellness solutions as well as create the right prompts so that the user gets the right information which they need. So what suggestions would you give to someone who is still starting in the field?
Yeah, okay, well, I think one thing that you could think about there, right? It's not, you don't have a human prediction problem so much, right? Or at least you're trying to map from prompt space to some kind of complicated human outcome,
yes.
right? So the first thing you need is data in order to be able to figure that out. And then I think one of the challenges with doing that sort of prompt optimization is that the space that you're optimizing over is much larger than the space that we're considering in these kinds of problems, right? So part of what made it possible for us to cover the space with the data set that we collected is that we have these relatively constrained sort of classes of problems. We have a recent, we have an effort underway at the moment where we're looking at more open-ended problems that can be described in text. And you can build similar kinds of models in those settings. It's just a little more complicated. But yeah, I think step one is you need a lot of data.
Thank you.
Hi, thank you for the very interesting talk. In the example with the trolley problem, you sort of showcase an example where both the black box model and the theory-driven model got it wrong. And the question is sort of in this extreme situation. I wonder, through the training process, have you encountered any situation where the black model got it wrong, but on the surface doesn't feel like an obvious outlier?
Yeah, that's a good question. We didn't look at that in that data set, but that would be a good complementary analysis to do, right? So that's something where what you would expect that would tell you is something about where your data coverage is poor, so it's generalizing poorly or something like that. Yeah.
Thank you.
Hi, Professor. My name is Patrick. I'm a student here. Thank you so much for the speech. And my question is something you mentioned during the time that you were extracting the theories from psychology. There's been a lot of papers, a lot of literature in the 100 years of histories of the development of these disciplines. And it means a lot to extract theories that are present in these literature. I'm wondering if there's, like, besides having graduate students read them and understand them and construct models of these theories, it would be possible for example, an automated pipeline for like mathematically modeling all these theories and testing them on pipeline.
Yeah, I mean, I think that's interesting, right? So so in the risky choice case, we were able to recapitulate a lot of that history in that single experiment. And you might expect that you'd be able to do similar things as you collect, large data sets in other settings too. One thing that we're interested in and have been thinking about is if you can use large language models to read the research literature to then generate hypotheses in these settings that then become meaningful classes of hypotheses to evaluate. And we've started to think about that, but that's obviously that's a good way to at least lighten that load. Yeah, but I mean, I think honestly, part of the point here is also there's relevant expertise, which is useful. This is part of my pitch. My pitch and my fear for psychology, right? So I think where psychologists have figured out a bunch of nuanced things about human behavior, but if we can't figure out how to leverage those nuanced things, they will become irrelevant in the face of sort of data-driven analyses. And so we need to work out for the future of that field how to find the right balance between theory and data. Yeah.
Thank you so much for the answer.
Thanks.
Hi, Professor. Thanks for the talk. I was wondering, so your work focuses a lot on specific scenarios. I was wondering if you've worked on or thought about modeling like the individual. So, given that they made this choice among these different scenarios, can we predict what they do for this scenario?
Yeah, so we have, I sort of quickly showed this plot, let's say here. So this is a slightly different data set. So in the previous data set I was showing you, we just focused on getting coverage of the choice problems. So we had those 13,000 problems, then we had about 20 responses per problem. We collected this other data set where we now have 1,000 decisions for each individual, and we can look at how well we can do in predicting those individual choices. And so what we're doing here is building a separate model for each individual. So each of these lines corresponds to what the utility functions and probability weighting functions look like for those individuals. And then we can also answer sort of questions about the population, like which, like there's meaningful variation in the extent to which they seem to do things like probability weighting across individuals. But in that data set, we can look at how much better do we get at predicting decisions, the more decisions we've seen for an individual, and how much better do we get as a consequence of modeling the population as well.
Right, different curves. Thank you.
Yeah.
Hello, Professor. Thank you for the talk. I was mainly interested in the method where you were talking about using pre-training data, mainly based on theory that you simulated. So I come from a data science background, so I understood the second part of it. Could you give me some guidance on where to look for or which theories to use to gather what kind of data?
Yeah, so in this case, the theory that we were simulating data from is the one that corresponds to this dashed line here, right? So we took the best fitting psychological theory, and we used that as the thing that we would then simulate data from. So you can actually think about this where you could have a pipeline where you say, come up with your interpretable, sensible, motivated theory, fit that theory to the data, then use that theory to generate a much larger data set that you use to pre-train your neural network, and then go back and fine-tune that neural network on the data, right? And all that you're doing is then making it so the neural network is instantiating the theory, right? The function that it's learned to correspond to is the theory, and then that becomes the starting point that you're using for the fine-tuning of the neural network itself. So the answer as to what theory you should use kind of depends on what problem you're solving, where you need to then, you've got a problem that you want to solve, you want to be able to learn in that setting, reading about the kinds of theories that people have had in that setting, gives you the information that you'd need in order to figure out how to generate the synthetic data.
Okay, that helps. Thank you.
Okay.
Hi, thanks for the talk. So over the past few years, there's been this proliferation of machine learning interpretability methods, things like causal interpretability and mechanistic interpretability. How much potential do you see in trying to open up some of these black box models and understanding what they're doing?
Yeah, I think that's definitely a thing that's worth doing, but I am a little skeptical about how well it will work in all of these settings, right? So often what you get out of that is something like some features that you're able to say, these features seem to be useful, right? The kinds of interpretability methods you use constrain the kinds of explanations that you can get, right? So you can get an explanation from that which says, seems like this feature is relevant, or it seems like this feature is relevant. And we did something like that for the sort of black box models that I was showing you. But I think taking an approach where we define the kind of explanation that we want in a way that corresponds to the sorts of theories that are normal in that domain gives us a richer set of options for being able to then pull something out of those models. So if I say, the thing that I really want out of this model is something which is going to fit this rational choice framework, and I want to find the best thing that is in this rational choice framework plus these extra features, that imposes a constraint on the classes of functions which I'm going to be using to try and approximate that thing. So what you're doing is you're building a sort of parallel approximation by building up that interpretable model class rather than trying to break down the features that are being used in the less interpretable one. So I think there's sort of parallel methods. It's more a matter of like what kind of explanation you're looking for. Yeah.
Cool, thanks.
Hi, Dr. Griffith. I was curious your thoughts on how you might model the utility function when there's multiple types of outcomes that people are weighing. For context, I'm researching the impact of colorectal cancer screening, and there's different types of modalities with different cost-benefit trade-offs. So colonoscopy is the most effective type of screening at preventing and detecting colorectal cancer. But a lot of people don't want to do colonoscopies. They'd rather do stool tests because they're less inconvenient and for people without insurance, less costly. Yeah, I was just curious about if there's even a possible way to model a universal utility function.
Yeah, that's an interesting question. So we have been starting to do something like that using, as I was mentioning before, text-based descriptions of decisions, right? Where we have some of those in medical context and we can sort of calibrate those against the actual preferences that people express. So I think, that's very like this, the sort of approach that's taken in the Centaur model that I mentioned, right? Where what you might do is start with something like a large language model and then try and fine-tune that on actual decision preferences that people express in order to try and figure out if you can predict the decisions that they'd make in those settings. And so in this model, there's nothing like a realized utility function, but it's doing something like, learning how to capture those preferences in a way that might be useful. Yeah.
Thank you.
Hi, thank you for this talk. I have a question that's a little irrelevant of the content of this, but I just was curious because you had a very early book about algorithms to live by and kind of the computational principles that we could learn from the algorithm. I was just curious when I was listening to this, now with the new model of the large language model, that can also simulate human behaviors, what is a principle that you would maybe add to the chapter of your book if you're writing one?
Oh, okay, that's interesting. I don't think I would change anything. So the point of that book was that for many of the kinds of decision situations people find themselves in, we know what optimal solutions to those decisions look like, right? So for things that are optimal stopping problems or explore-exploit problems or these kinds of very common kinds of problems people encounter. So the real focus on that book was on these kind of rational solutions that people might not think about, but also a different way of thinking about what rational action is, which takes into account the effort that you put into trying to decide what you're going to do, right? And so I have a whole other line of work which is about that, trying to understand how people navigate those trade-offs and try and come up with a better characterization of what we call resource rationality, which is figuring out how to allocate computational resources to making good decisions. In terms of the things that I talked about here, though, I think the one thing that some of these things might do is help you to understand how it is that people are able to make reasonable decisions outside the settings where those optimal solutions apply, right? So the big problem that we encounter when we try and use those optimal solutions is that not every decision problem that people face is one that sort of fits into the schema of one of those optimal strategies. And despite that, people are pretty good at coming up with strategies that they'll use for making decisions in new situations. And so that's the kind of thing that I think some of these things like the large language models might be helpful for, is thinking about how to solve those kinds of problems of interpolating between optimal cases to find what are reasonable decision strategies might look like.
Yeah, real curious about the detail for the fine-tuning. As you know, there are two different ways of fine-tune, supervised fine-tuning or reinforced learning with human feedback. I was wondering, which one's used.
Yeah, this is supervised fine-tuning, and it's using LoRa, so it's like making it a little bit easier to fine-tune the model. Yeah. Okay. All right, thank you. Thank you.